Welcome. This is Professor Nathan Weezy of Marquette University, and this is Digital Control of Power Electronics. This section, we're going to continue talking about the digital controller for current mode control of a buck-boost converter. Where we left off last section, we have designed this controller, but only in the continuous fashion. In this section, we will design the controller in the digital domain and look at kind of the trade-offs between sampling time and the different approximations from continuous time to the discrete digital domain. So what we're going to design today is our digital controller here, and we'll do that by converting our continuous time controller to a digital controller. So where we left off, again, classically we have this buck-boost converter shown here in black, and the blue is really just the surrounding control structure. And let's just recall how we did the whole design process. Essentially, these lines set up our buck-boost converter parameters. And so this just describes we were doing input voltage of 10, outputting 10 with 50 microhenry inductance, a capacitor of 247 microfarads, 10 milliohm ESR, output power 20 watts, switching frequency at 200 kilohertz, and an output load resistance of 5 ohms. And what we did down here from lines 27 to 26 is just define the plant transfer function. Essentially, this tells us how the output voltage reacts to small perturbations in inductor current. And then we have our controller design parameters, which are adjustable. And lastly, we ended up last section here, which was the controller design. So once you select, for instance, your bandwidth and your phase margin, you get here and you have your controller design. And what this is essentially saying is that we'll have our pole and zero location and the gain of the controller or the integrator at the completion of line 47. So KC will be selected, FZ and FP, which are pole and zero. Those will be all selected, and we'll have our general control structure here in 47 defined. Now at this point, what we'd like to do is convert this continuous time controller to a digital controller and then implement it and see how the system responds. In terms of digital controllers here, we're going to explore a couple different variants. We're going to do a 10 kilohertz sample time. That means we're going to only update the digital controller at 10 kilohertz or every 100 microseconds, whereas the switching frequency is 200 kilohertz. And then we'll also consider controllers at 50 kilohertz, so they'll update their values at 50 kilohertz, which is 4 times slower than switching frequency at 200 kilohertz. We'll do this for 3 different types. Here we'll have backward dealer. And we'll also do zero order hold and Tustin. And we'll do the same for this other frequency at 50 kilohertz. So we have zero order hold, we have Tustin, and we have backward dealer. And what we'll do is just kind of check out the response to all these different types of transformations and how they respond. So the first response we'll look at is shown for this controller shown here, which is backward dealer at 10 kilohertz. And first thing you can say from the output voltage is this is severely underdamped. But you can actually see it is converging down back to 10 over a really long time relative to our bandwidth. So it's not unstable in the sense that the output voltage is going to oscillate. It's just this is a pretty poor design. We generally wouldn't want, for instance, almost 2 volts of undershoot and a volt of overshoot and significant length of ringing. So although the system would eventually converge back to 10 volts without another transient, this is essentially not a very good controller design. And again, let's just recall we're jumping from 10% load up to 100% load in this example. And you can see the same oscillation happening with IL. It tracks the output voltage. The other thing you can see is our discrete steps of updates. Well, this is done at 10 kilohertz. So it goes without saying here, you can clearly say that we would probably like to update our control at probably a faster rate, and we definitely could. IL has no problem tracking at a higher frequency. You can see that here. And down here in the last graph, this is just IL star. This is what we are commanding for IL, and of course the middle graph is what it actually is. So you see good agreement between them. But just overall, not a very good controller design. Let's consider now 10 kilohertz, but we'll go to a Tustin approximation for designing the controller in the digital domain. And you can see now this one responds a lot better than the previous one, but you still see doesn't look very clean. It's still underdamped. Although it's better than the previous one, this is generally not a great response either. And you can see these discrete steps in the IL current. Again, this is just saying that we could probably update the IL current command faster and still be able to track IL. Okay. So we're underdamped here. We're underdamped here. So let's consider the higher frequency controllers and see if we get any better response. All right, now we're back to backwards Euler, but now we're at 50 kilohertz. And you can see now, you still actually, if you zoom in here because of how fast the current controller is, you can see these discrete steps. They're at 50 kilohertz. You can also see the output voltage dips down way less, only to slightly beyond 9, and then comes back up. So the response is very well damped. Now you may not want this much voltage drop. Or let's say maybe you want 100 millivolts or less. Well, there's a couple ways to attack this. You can increase the capacitance, redesign your controller, and you can also decrease your inductance so your current responds faster. So you can decrease this so your current responds faster. You can also increase your bandwidth. So these are all levers that you have to essentially make this drop not so fast. So if you increase your bandwidth, what happens is, if you think about increasing bandwidth, is this IL will go up faster, straighter like this. And the faster this goes up, the quicker we can replenish current in the output capacitance so that you don't lose all this area in terms of charge on the cap. So those are just different strategies for essentially making this transient less affecting the output voltage. And again, this last plot here is IL star, what we are commanding the current to be, and you should see good agreement between these two, the actual and what we're asking for. All right, lastly, we'll do Tustin at 50 kilohertz. Just kind of visually comparing these two, you don't see much of a big difference. This is a almost 1 volt undershoot, and this may not be acceptable for your application. So essentially, again, you're going to have to increase C, decrease L, increase bandwidth. You don't have to do all these at the same time. You can do them separately. It just depends on. In general, increasing capacitance is okay. It does change your controller. You'll have to redesign it because it changes your plant, but it just costs more, and generally that's not the first thing you attack. Maybe you attack lowering the inductance so you can push the current up faster, make this current rise faster, or increasing the bandwidth. That comes pretty free. You just got to make sure you can stabilize it. Lowering the inductance does come with another advantage. If you lower the inductance, you essentially it should be a cheaper component because it should be a smaller component, lightweight and less material. You also can increase the bandwidth by decreasing L because you have less inductance, which means you can step this current up. Now, There is one trade-off you want to be aware of. The more and more you lower this, the wider range that you may enter DCM in, and you may or may not want to be in DCM depending on your application. But these are all things you want to consider when designing the controller. This last plot here is the control effort, so I don't really need to cross that out, but the control effort here is really just IL star, what I'd like to command the current to be. So this is just taking a look at 4 different controllers. We did 10 kHz and 50 kHz, both Tustin and backwards Euler, and looking at their responses. Let's take a look at kind of all 5 of those now, plotted on top of each other, and you can kind of see the effect of all these at a moment's glance. So again, this red one was backwards Euler, and this was 10 kilohertz. The other one, what was the other one at 10 kilohertz? It looks like it's kind of orangish yellow. That one would be this one. This was 10 kilohertz Tustin. Even that one, even though it was at the same frequency, that one had a much better response than the backwards Euler. That one rang for quite a bit. Remember, blue is your continuous time response. If we kind of zoom in, the one that, there actually isn't one that really tracks that one all that well, but this blue is our continuous time one. I'd say, I guess green is probably the closest to that. And we don't have to mimic the continuous time response exactly, but just to be aware of that there's going to be differences. So this one seems to track in terms of output voltage the best with those. But even when you go to the digital domain, you can see that you have an overshoot in the inductor current, whereas in continuous time in blue, you see that it's pretty well damped. So that's interesting to note here. You're always going to kind of get that because we have some phase delays and other things that we haven't accounted for in our digital control loop yet, and we haven't really considered quantization, so we're not getting great agreement here, but that's okay. And if we factor that stuff in, we'll have a pretty good design. And as is already, these backwards and Euler and Tustin at 50 kilohertz are giving us a pretty decent response, having all things considered. If we look at the control actuation output too, another thing you can see here is that the green and purple waveforms are essentially delayed, and that's just the digital delay that is present in digital systems. So you can see like the continuous time controller starts actuating right away, whereas the digital ones take at least 1 to 2 cycle delay, and it depends on what the sampling frequency is and all that good stuff. So okay, this concludes the design of a digital controller for current mode control of a buck boost converter. Thank you.